Okay, so this lecture is going to focus on the fourth feature of a proton NMR spectrum, which is the splitting or the number of peaks in each signal. We're going to learn what that represents and how to use that. And then at the end of today's lecture, we're going to put all of this information on proton NMR together and discuss how we're going to use that to determine the structures of unknown molecules. So on the screen, we have a sample molecule. Okay, this is 112-tribromoethane. And from the last lecture, you should easily be able to look at this and see that it has two different types of hydrogens. And we see that the CH, or the methine, that's attached to, the carbon is attached to two bromines, that's going to be more de-shielded, so that'll show up further downfield. And then the CH2 that has one bromine attached is going to be upfield, kind of in the middle of the spectrum in this case. If we had integration data, we would see that this signal is twice as big as that signal. But what we're focusing on here is that the CH signal is a triplet. It's split into three peaks with a 1:2:1 ratio. And the CH2, or the methylene, is split into two peaks. It's a doublet. And the ratio of heights in the doublet is 1:1. Okay? So this is what we refer to as splitting, or sometimes it is called spin-spin splitting, because it is the spins of the hydrogens that are causing the splitting of the neighboring protons. So what we find in proton NMR is that neighboring protons that are not equivalent to the protons in question will cause splitting of the signals. And when we say neighboring, we mean protons that are on adjacent carbons or non-equivalent protons that are on the same carbon as that hydrogen. So for hydrogens to split each other, they have to be separated by 3 sigma bonds or less. And in this molecule, tribromoethane, we see that the hydrogens are separated by 3 sigma bonds. If hydrogens are on adjacent carbons, they will be separated by 3 sigma bonds. So we need to understand why non-equivalent neighboring hydrogens will cause splitting of signals. And it has to do with the fact that these protons have their two different nuclear spin states, the +1/2 state and the -1/2 state. So depending on the orientation of the spin, the magnetic field created by that spinning nucleus is either going to be lined up with the applied magnetic field, or it will be opposing the applied magnetic field. If a neighboring hydrogen is within 3 sigma bonds, then it can actually feel the effects of the different spin states of those protons. So here, let's focus on why the CH2 signal is a doublet in which the two peaks are a ratio of 1:1. So we have the two nuclear spin states of the CH, or the methine hydrogen. We can either have that nucleus spinning in a way that causes the induced magnetic field to be lined up with the applied magnetic field, or we can have that nuclear spin state in the orientation that causes the induced magnetic field to oppose the applied magnetic field. Okay? So the CH2, those protons are within 3 sigma bonds of the CH, so they are close enough to feel the effect of the two different nuclear spin states. So that's what leads to 2 peaks in the signal. So we're going to have one peak that is due to the molecules that have the CH nuclear spin state aligned with the applied magnetic field. So that's a de-shielding effect, leading to a higher chemical shift. And then we're going to have a set of molecules that will have that nucleus opposing the applied magnetic field. And they will show up at a lower chemical shift value or upfield. I didn't do a great job of drawing these. This one is fatter than that one. They should be the same width and the same height. That is due to the fact that the energy differences between these nuclear spin states is very small. I mentioned this in our lecture before Thanksgiving. And so that leads to very close to a 50-50 ratio or a 1-to-1 ratio of the two nuclear spin states. So in our 1,1,2 tribromomethane sample, approximately 50% of the molecules will have this CH in the spin state where the induced magnetic field aligns with the applied magnetic field, and the other 50% will have the nuclear spin state where the induced magnetic field opposes. So that leads to these peaks having the same intensities and the same heights. Okay, so when we have one neighbor, then we are going to have a doublet. The peak will be split into a doublet by that one neighbor due to these two different spin states that we have. Okay? So now hopefully we understand why the CH2 signal is a doublet. It's split into a doublet by its one neighbor. Why is the CH signal or the methine signal a triplet? Why is it split into 3 peaks? And why is the ratio of those peaks 1 to 2 to 1? Well, the CH has 2 neighbors, and so we have to consider the combined effects of the spin states of those 2 neighbors. How many different combinations of spin states could we have with 2 protons? Well, we could have those 2 protons both being aligned with the applied magnetic field. We could have one aligned and one opposing. And there's 2 ways we can have that. We could have up, down, and we could have down, up. Okay, so there's 2 different combinations that give the same result. And then we could have both of the spins opposing the applied magnetic field. Okay, so that gives us 3 different possibilities. So this one is going to be downfield at a higher chemical shift than what we would expect just based on the applied magnetic field. Here the spins cancel each other out, and then here the spins are shielding. So we end up with 3 peaks in a 1 to 2 to 1 ratio. Okay, and that's what we see right here. Okay. Now the distance between these peaks is important. That is known as the coupling constant, or the J value. Okay, J value or coupling constant. Okay, the distance between those peaks is measured in hertz. And a typical value of J or coupling constant is anywhere between 0 to 18 hertz. And later on in today's lecture, we'll talk about the significance of J values. So here we have our triplet. It's going to look something like this. And J can be measured as the distance. I did a poor job of drawing these brackets, but hopefully you see what I mean. J can be measured between these 2 peaks and these 2 peaks, and it's going to be equivalent. Okay. And then another thing about coupling constants or J values that's very helpful is that hydrogens that are splitting each other will have the same J values for their signals. So the CH2 in tribromoethane is splitting the CH into a triplet. The CH is splitting the CH2 back into a doublet. And so what that tells us is that the J values for these peaks will be identical. Okay, so we could measure those J values, and in a more complicated molecule, we could see which signals are splitting each other, which hydrogens were adjacent to each other. Okay? So An important thing to note, and we'll come back to this, is that splitting only occurs when these adjacent hydrogens are not equivalent to each other. So what do we do if we have more than two neighbors? Well, if you're a math whiz, you can see that the pattern we're following follows a Pascal's triangle sort of relationship. And there's a formula, the multiplicity formula, which is n plus 1, where n equals the number of non-equivalent neighboring hydrogens. Okay? So if we have one neighbor, then the peak is split into a doublet. If we have two neighbors, the peak is split into a triplet, and the ratio is 1 to 2 to 1. That ratio is what comes from Pascal's triangle. This table here is taken from a textbook that is used in Chem 455, which is an excellent class that I strongly recommend if you're interested in learning more about NMR spectroscopy. And then if we have three neighbors, if we have a methyl group that is adjacent to our hydrogens, then the peaks will be split into a quartet according to this formula that we have here, because n will be 3 and n plus 1 will be 4. The relative ratios of those peaks will be 1 to 3 to 3 to 1. And that comes from this analysis here, considering the different combinations of spins that we can have when we have 3 protons, okay? You see, if we do the same kind of analysis that we did for having 2 neighboring protons, but we apply it to 3, then you will get this sort of a pattern that we see here. And then you see over here how we would measure J, or how we would measure the coupling constant if we had a doublet, a triplet, or a quartet, okay? So singlets, doublets, triplets, and quartets, those are our most common types of signals that we see. We can have more neighbors in some cases. We'll see a case where we end up with, so they goofed this up a little bit here. This is supposed to be a heptet, and that's supposed to be an octet. I just noticed that they goofed that up. But we'll see a case where we see a heptet where we have 6 different neighbors. All right, so we have here a table in the book that shows us common splitting patterns that we would see in the proton NMR. And it's important to note that HA and HB have to be non-equivalent to each other in order to be splitting each other. And these lines that we see that have nothing attached to them, those have to be non-hydrogen atoms. They have to either be carbons or heteroatoms, right? If these are hydrogens, then the patterns would be different, okay? So this would be a molecule where you'd have 2 CHs or 2 methynes next to each other that are not equivalent. You would have a doublet pattern and so forth, okay? This one is common. It's common to have an ethyl group in a molecule. You'll see a quartet and a triplet whenever you have an ethyl group. The CH2 is going to be the quartet, and the CH3 is going to be the triplet, okay? This one right here, number 3, again, I'll emphasize this. You only see this pattern if these CH2s are not equivalent to each other, okay? How many type of hydrogens in this molecule? 1,2-dichloroethane? Just 1. These CH2s are equivalent to each other. You will just see a singlet in this case. Equivalent neighbors do not split each other. When neighbors are equivalent, they cannot impact each other's spins, or they cannot feel the impact of the spins. They cannot impact the signals. You would see 1 singlet in this case. But if we replaced one of those chlorines with a bromine, now these 2 CH2s are different. Now we would see 2 triplets, okay? So this is an important concept to understand when we're looking at the patterns that we see in the proton NMR and in this table. So there's a common pattern that's not shown in this table, and that is when we have an isopropyl group. These two methyl groups are equivalent to each other. And so the CH here has a total of 6 neighbors, six neighbors that are equivalent to each other, but not equivalent to that hydrogen. So that's going to get split into a heptet or a septet. Honestly, I'm not sure exactly what they say for that, but we see our 7 signals here. They've expanded this signal so you can see them. And then the methyl groups have a single neighbor, and so they're split into a doublet. So whenever you see that septet and doublet pattern, that's characteristic of an isopropyl group, okay? And you notice the chemical shift of this methine is impacted by the chlorine that is attached, okay? So far we've looked at hydrogens on adjacent carbons that are splitting each other. But non-adjacent hydrogens on the same carbon can also split each other, okay? So let's take a look at this molecule. HA and HB are non-equivalent to each other. A is cis to the chlorine, trans to the bromine. B is cis to the bromine, trans to the chlorine. So since these are non-equivalent and they're neighbors, they're connected by 3 sigma bonds or less. In this case, they're connected by 2 sigma bonds. Then they will split each other. So we would see 2 doublets in the proton NMR of this particular molecule. And if we look at a spectrum, it's not blown up very well, but if you zoom in really closely, you'll see that each of these signals is a doublet and is reflective of the coupling between these 2 hydrogens, or the splitting that each of those hydrogens does to each other due to those 2 different nuclear spin states. As we'll learn in a few minutes, when you have hydrogens on the same carbon of an alkene that split each other, the J values are very small. That's why it's hard to tell that each of these signals is a doublet, okay? So here's another molecule similar to the one we showed you previously. This is isopropyl bromide with our septet and doublet pattern. So here, HB has 2 neighbors that are equivalent to each other. Each of these methyl groups is equivalent to each other. And so following the n+1 rule, we get a septet for HB. However, when you have 2 different sets of neighbors, 2 sets of neighbors that are not equivalent to each other, the coupling pattern is a little more complicated, okay? So here we have 1-bromo-propane. Let's do the easy ones first. HA is going to be a triplet. We see that right here. HC is also going to be a triplet. We see that right here. We know this is HC because it's de-shielded due to the impact of the bromine. HB is actually a multiplet, okay? That's a term that we use when the splitting pattern isn't very neat, when it's kind of messy. And that's what happens when we have non-equivalent neighbors, okay? This figure's not in your current edition of the textbook. This is from an earlier edition of the textbook. Your textbook kind of glosses over this issue, so it's important to pay attention as we have this discussion. So HB has 2 different sets of neighbors. It has 3 hydrogens in the methyl group of HA and 2 hydrogens in the methyl group of HC. And the coupling constants, or the J values, do not have to be equivalent when you have different types of neighbors. And that can give you a more complicated pattern. So here's a figure, again, from an earlier edition of the textbook that shows you what happens when you have non-equivalent neighbors and you have different J values or different coupling constants. What you have to do is consider the impact of those non-equivalent neighbors separately. So let's start with HA, the methyl group. HA is going to split HB into 4 peaks. We apply the n+1 rule, and we end up with 4. Okay, so we create something that looks like that we call a splitting tree. We initially would pretend that that signal HB would be a singlet, but we know it's going to be split into a quartet by the methyl group, and the ratios of these peak heights are going to be 1 to 3 to 3 to 1. The distance between those peaks is going to be the coupling constant between HA and HB. Now we need to consider the impact of HC on HB. HC is going to split HB into a triplet if we apply n+1. But because we've already split it into a quartet, what we're doing is splitting each of these 4 peaks into a triplet. Okay? So we end up with a quartet of triplets, a total of 12 peaks. The distance between the hydrogens in each of these 4 triplets is going to be the coupling constant between B and C. Okay? So we get a more complex pattern when we have non-equivalent neighbors and we have significant differences in the coupling constants between those different neighbors. Okay? So we end up with a different multiplicity rule. Instead of n+1 telling us the number of peaks, we have to use n+1 times m+1. And what that's going to tell us is the maximum number of peaks in the signal. Okay? So where we had 3 of one type of neighbor, n+1, that's going to be 4. 2 of the other type of neighbor, m+1 is 3. 4 times 3 is 12. We could see a total of 12 peaks in HB. Okay? So it's important to note that we only see all 12 of these peaks when there's a big difference in those coupling constants or those J values. As JBC, if it were to increase and get closer to the value of JAB, what would happen is some of these peaks would start to overlap. You'd see a bigger distance between the peaks in these triplets, and you'd start to see overlap between those triplets. So you'll see less of those peaks, lower number of peaks, okay? And if we have an acyclic molecule, such as 1-bromopropane, the J values are very, very similar. So you're going to see something that closely resembles the n+1 pattern, where we would take 3 and 2 and add that together, get 5, and add 1 and get 6. We'd see something much closer to a sextet than to this quartet of triplets for this molecule. But it wouldn't be precisely a sextet because these coupling constants would be slightly different from each other. So we would refer to it as a multiplet. That's why we use the word multiplet here in this case instead of sextet. Your textbook has glossed over this issue and calls it a sextet, which it is not. Okay? So when do we see these more complicated coupling patterns? We see them when these J values are very different from each other, and that occurs most frequently in rings and alkenes. When we have rings and alkenes, we have a wider range of J values than when we have acyclic molecules. And so as a result, we would see more complicated coupling patterns. Okay? So let's talk about alkenes now in more detail. Different hydrogens and alkenes will have very characteristic J values, and we can use those J values to identify their signals in the proton NMR. So if we have hydrogens in an alkene on the same carbon that are not equivalent to each other, Those hydrogens are geminal. So we'll refer to this as J geminal, or the coupling constant for geminal hydrogens. And that's going to be very small, in the range of 0 to 3 hertz. Okay? If we have non-equivalent hydrogens on adjacent carbons of an alkene, and they are cis to each other, they will have a medium range value for their coupling constants in the 5 to 10 hertz range. And then if we have non-equivalent hydrogens that are trans to each other in an alkene, they will have a large value for their coupling constant. The trans coupling constant will be usually between 11 and 18 hertz. Okay? So the reason for this is related to the fact that the magnitude of the coupling constant is related to the dihedral angles between those hydrogens. Okay? If you take Chem 455, you'll learn more about that in more detail. But for now, we'll just say that the coupling constant is related to the dihedral angles, which are different in these cases. Here you don't really have a dihedral angle because these are on the same carbon. But you have those different relationships between those nuclei in space, leading to different values of the coupling constants, or J values. So here are some consequences of that. So if we look at this molecule, these two diastereomers, let's say we knew that we had a sample of chloropropanoic acid, but we didn't know if it was the E isomer or the Z isomer. In the E isomer, those hydrogens are trans to each other, so we would expect a larger J value than if we had the Z isomer, where those hydrogens are cis to each other. So we could acquire the proton NMR spectrum. We could pick these hydrogens out easily, right? The only other hydrogen is this carboxylic acid. That's going to be way downfield in the 10 to 12 range. And so the one that had the larger J value would be the trans isomer, or the E isomer. The one that had the smaller J value would be the cis isomer, or the Z isomer. So it'd be very easy to tell those two compounds apart based on the coupling constants, or the J values. If we had a monosubstituted alkene, the situation would be a little bit more complicated, but we could still use J values to assign the positions of the different signals in the proton NMR spectrum. So let's take a look at this molecule. So this is an ester. We have a CH3 out here, but the hydrogens that we're interested in are the hydrogens on the alkene. Okay? And we're just going to call them A, B, and C. Okay? So all three of these hydrogens are different from each other, right? None of these hydrogens are equivalent to each other. The two that are on the same carbon are different because one is trans to the oxygen and one is cis to the oxygen. So we have a case of each of these hydrogens having non-equivalent neighbors, right? If we look at A, B and C are the neighbors, but they're not equivalent to each other. So we have to apply the more complicated formula, the n+1 times m+1 formula, to determine that each of these hydrogens is going to have 4 peaks in its signal. And we're going to refer to those peaks as a doublet of doublets. Because what we will say, if you remember the tree that we created, we will say that B is going to split A into a doublet, and then C is going to split each of those 2 peaks into a doublet. So we end up with a doublet of doublets. Our example here on the screen, we had a quartet of triplets, so this will be a simpler example. We'll have a doublet of doublets for each of these 3 peaks, for A, for B, and for C. Of course, the one I haven't labeled, maybe I'll label that D, HD is just going to be a singlet. Okay, so that'll be easy to spot in the NMR. How are we going to tell these three doublet of doublets apart from each other? We can do so by considering the different J values that we will have for the different types of relationships. So let's look at HA. HA has a geminal neighbor. That geminal neighbor is going to have a very, very small J value. So one of our doublets is going to have a small J value. And then the other neighbor is cis. Remember, we said that the cis J values in alkenes are medium. So we're going to have a small coupling constant and a medium coupling constant for the signal corresponding to HA. Now let's look at HB. Has a geminal neighbor. We'll have a small coupling constant. It has a trans neighbor. That will give rise to a large coupling constant. Okay. And now we look at HC. HC has a cis neighbor. That gives rise to a medium J value. And it has a trans neighbor. That's going to give rise to a large J value. So each of these signals will be a doublet of doublets. It will have 4 peaks, but each of those signals will look different because of the different magnitudes of those coupling constants. So let's go ahead and take a look at the spectrum and see what we mean by that, okay? This molecule has a common name. It's called vinyl acetate. As we go from left to right, you see that they've helpfully expanded each of these signals so you can actually see them. And if you look at HD, you see that the peaks are much more spread out than what we have in B and C. So what that tells us, see, they've used different letters than we have on the board. Sorry about that. But this particular signal has a medium J value and a large J value. It's missing the small J value. You can tell because with B and C, you have pairs of doublets, and within those pairs, you have very, very small J values. So these are the ones that have the small J values. This is the one that has the medium and the large J value. So you can look at this and say, aha, that has to be the hydrogen that's by itself. It doesn't have another hydrogen on its carbon. That's the one that we labeled as C, the one that is next to the oxygen. Okay? Now we look at these two signals, and you see that the pair of doublets is further apart from each other in B, what they're calling B, than it is in what they're calling C. So that tells us this is the one with the small and the large J values. This is the one that has the small and the medium J values. So this one is trans to the neighboring proton. Sure enough, the way they've labeled it, you see that it's trans. This is the one that is cis. Sure enough, you see the way they've labeled it, it's cis. And of course, the singlet, that's easy to spot. The methyl group has no neighbors, and so no splitting. So notice we were able to assign all of the hydrogens in vinyl acetate to peaks in the proton NMR without even looking at the chemical shift data. All we did was look at the splitting and the J values. So this is where those J values are very, very powerful, where they're very, very helpful to us. However, we could use the chemical shift to check our work. You notice that this signal, the one they're calling HD, is much further downfield than any other signal in this molecule. And we would expect that because that is the hydrogen on the sp2 carbon that is bonded to an oxygen. So it is de-shielded by both the pi electrons of the alkene and the oxygen that is also attached to the same carbon. So as we would expect, we have a significantly different chemical shift for HD, whereas B and C are fairly close to each other. Okay? So this is an example of how splitting data, J values, differences in J values can help us assign peaks in an NMR. Okay? Very, very useful for us. All right, our next example is ethanol, molecule we've talked about before. And when we look at the spectrum of ethanol, we get a bit of a surprise. What we see is the OH signal is a singlet. We would expect the OH signal to be a triplet. And then the ones that they're calling HB are just a quartet, meaning that HB is split only by HA, only by the methyl group. It is not split by the OH. And the OH is not split by its neighbor. So this is a general principle. Protons that are on oxygen or nitrogen are not split by their neighbors, neither do they split their neighbors. Okay? The reason for this is that these protons can rapidly exchange from one molecule to another. So if you have a sample of ethanol dissolved in deuterated chloroform, used for taking an NMR spectrum, as those ethanol molecules collide with each other, you're going to have exchange of the protons. The protons are going to, an individual proton is going to hop from one molecule to another quite rapidly. You're also going to have trace water present in the solution because it's impossible to get rid of water. So water molecules can serve as a shuttle, shuttling protons from one molecule to another. So the consequence is that an individual proton does not attach to an oxygen, does not remain on a single molecule long enough for its neighbors to feel the impact of its nuclear spin state. So when you have OH or NH protons, because they're rapidly exchanging from one molecule to another, their neighbors do not feel the impact of their different spins. And those protons themselves do not feel the impact of the neighboring spins. They're just not on an individual molecule for long enough. So we do not see splitting in those cases. Okay? For reasons we don't get into, those peaks, OH and NH peaks, are usually broader. They're usually broader, fatter than what we see in this particular spectrum. But they are singlets. They don't undergo splitting. Okay? All right, let's talk about cyclohexane. How many different types of hydrogens do we have in cyclohexane? Okay, we have two different types of hydrogens. We have our axial hydrogens, and we have our equatorial hydrogens. So all of the axial hydrogens would be equivalent to each other. All of the equatorial hydrogens would be equivalent to each other. You could try the d-test and find this out. So how many signals do we have in cyclohexane? The answer is not 2. The answer is 1. So why do we only see 1 signal instead of 2? The reason is that we have very rapid ring flipping. I'm going to change these from axial and equatorial to A and B to show you that what happens when we do ring flipping is the axial and equatorial hydrogens exchange with each other. So when we ring flip, B is going to go from equatorial to axial. A is going to go from axial to equatorial. So the two different hydrogens of cyclohexane are rapidly exchanging with each other. And this rapid exchange with each other prevents us from differentiating them in the proton NMR. So whenever you have hydrogens that are rapidly interconverting or exchanging with each other, those are going to appear as a single signal in the proton NMR. We're not going to be able to distinguish between them. So in cyclohexane, we'll just see 1 singlet in the proton NMR. However, if you were to cool this way, way down to a low temperature, let's say about minus 100 degrees Celsius, you could actually slow down the ring flipping enough that you would be able to see 2 signals. Okay, so if you make that ring flipping slow enough, that exchange between the protons is slower than the pulses that we're delivering of the radio frequency radiation, then you could actually see the 2 signals. But most of the time, you're just going to see 1 signal the message here, the lesson we're learning here is that whenever you have hydrogens that are rapidly interconverting, they will be equivalent in the proton NMR. Okay, let's look at another example that will teach us another principle. This is a generic monosubstituted benzene ring. Okay, we see three different types of hydrogens in a monosubstituted benzene ring. We have a plane of symmetry down the middle. So we have HA, HB, and HC. So we would expect there to be three different signals in the proton NMR spectrum of a monosubstituted benzene. What would HA look like? Each HA has one neighbor, so we would just apply the n+1 rule. So HA would be a doublet. HC has two neighbors that are equivalent to each other. So HC would be a triplet. Each HB has two neighbors that are non-equivalent to each other. So if the J values were substantially different, we would see B as a doublet of doublets. If the J values were identical, we would see HB as a triplet. And if they were close, it would look like a triplet, but not exactly be a triplet. So the identity of B would be different, could be either a triplet or a doublet of doublets, but A would be a doublet, C would be a triplet, and you also have integration that you could use to identify these signals, right? A and B would each integrate to two hydrogens, whereas C would integrate to one hydrogen, okay? So here we see the spectra of three actual monosubstituted benzenes, and it's only showing the region of the aromatic hydrogens. It's not showing the other hydrogens in the molecule. But we're not seeing three signals. We see two signals here for ethylbenzene. We do see three signals for benzaldehyde. That's good. But we only see two signals for methoxybenzene. So what's going on here? This goes back to what I mentioned in our previous lecture, which is that when you have types of hydrogens that are different from each other, but similar, sometimes they overlap. Okay? So what you're seeing here is overlap between two of those types of hydrogens. Over here, you're also seeing some overlap. Okay? So we're not seeing the neat patterns. Here we see the neat pattern. We don't have that overlap, but they're pretty close together. So that's the take-home message from this example, is that in practice, the overlap of peaks can cause more complicated patterns to appear than what we would otherwise expect. Okay, so the last thing we're going to talk about in this lecture is how we take all the information we can get from a proton NMR and use it to identify the structure of an unknown compound. So here we have a spectrum of an unknown compound, and they've given us the mass spec data and the IR data. We've already looked at the mass spec and we've already looked at the IR. So we've already determined a molecular formula, C4H8O2, from the mass spec data. And the IR has told us that we have a carbonyl group. So we know we have a carbon-oxygen double bond, okay? If we look at that formula, how many degrees of unsaturation? We've got 1. And so we know that that 1 degree of unsaturation is taken up by the carbonyl, the carbon-oxygen double bond. So there are no other double bonds or rings in this molecule. So we're going to go through a 4-step process to determine the structure of this molecule. I've said this a couple of times before. There's more than one way to solve a spectroscopic problem. More than one method that you can use. If you come up with your own method that works well for you, then please go right ahead and use it. But the method that I'm going to show you is one that I think is logical and one that works very well. So this is a good one to use if you have other ways of, other orders in which you consider the data and can use the data to propose a structure, that's fine. But we're going to go through a system here. And this is what you would do after you've looked at the mass spec and the IR. I would look at the mass spec first and come up with a molecular formula. I would look at the IR second to figure out some functional groups. From the IR here, we figured out we have a carbonyl. And then the first thing I would do after looking at the proton NMR is determine the number of different types of hydrogens. Okay? This is the easiest thing we can do from a proton NMR. We simply have to count the peaks, assuming there's no overlap. Or the signals, I should say. So we have 3 different signals in this molecule. So we have 3 different types of hydrogens. Okay? Once we've done that, we're going to use the molecular formula and the integration to determine the number of hydrogens in each signal. Okay? So they've given us a molecular formula. We know we have 8 hydrogens in this molecule. They've given us integration units. We add those up and we get 40. Okay? We don't do a whole lot of math in this class, but hopefully you can divide 40 by 8 and find that there are 5 integration units per hydrogen in this molecule. Okay, so knowing there are 5 integration units per hydrogen, we can look at each of these signals and figure out how many hydrogens are represented. This first, well, let's go from right to left. So C is going to have, we divide that by 5 and we get a number pretty close to 3. So we're going to draw this over on the sideboard. That tells us that we have a methyl group. That's a CH3. Okay. B, we divide 11 by 5. That's pretty close to 2. That tells us we have a CH2. Sorry, I broke the chalk. Okay. And then we look at A, 15 divided by 5, that gives us 3. That tells us we have another CH3. Okay, so our hydrogens, our 8 hydrogens, are going to be present in 2 different methyl groups that are not equivalent to each other and a CH2. Okay. The other thing we can do as part of this is we can look at what else is present in the molecule. We've accounted for 3 of our carbons. There's 1 more carbon. We know that that carbon is part of a carbonyl. So we can draw a carbonyl group. Okay. And these are not methyls. I'll just put squiggly lines indicating that this carbonyl is bonded to something which may or may not be these methyl groups. Okay. So now we've accounted for all 8 of our hydrogens. We've accounted for all 4 of our carbons. But we have 2 oxygens and we've only accounted for 1 of them. We know there's no more degrees of unsaturation, so we know that that other oxygen has to be an sp3 oxygen and has to be bonded to 2 other groups. Okay? So based on these 2 points and what we got from the mass spec and the IR, we've generated these 5 different fragments. And now, as we go forward, we need to figure out how to connect those fragments together to come up with actual structures. Okay? So our third point, we're going to use splitting patterns to determine connectivity. Okay? So the first thing that jumps out at us is we have a quartet and a triplet. Whenever we have a quartet and a triplet, we know that we have an ethyl group, and we know that the CH2 of that ethyl group doesn't have any neighbors on its other side. So what that means is we can take our CH2 and one of our CH3s and we can put them together. Our splitting data allow us to say that we have an ethyl group. This ethyl group has to be bonded to something that has no hydrogens on it. Otherwise, the CH2 would not be a quartet. And then we know also that our third set of hydrogens, our other methyl group, has no neighbors, no neighboring hydrogens. Okay? Fortunately, we have fragments of this molecule that have no hydrogens on them. We have our carbonyl and we have this oxygen. Okay? So that tells us that these functional groups have to be connecting our ethyl and our methyl groups. So how could they do that? There's two ways that could be possible. So we could have our ethyl group, we could have our oxygen, our sp3 oxygen, that could be bonded to our carbonyl, which could then be bonded to our methyl group. Okay, that's one possibility. The other possibility is we have the methyl group bonded to the sp3 oxygen, connected to the carbonyl, and have that then connected to the ethyl group. Okay, so how do we distinguish between those two possible structures? That's where we get to the fourth point, where we now use the chemical shift data to differentiate between possible structures. Okay, so let's go back to our proton NMR. And based on our knowledge of chemical shift, we would expect the signal that is the most deshielded or the most downfield to be the one that is attached to our sp3 oxygen. We see that that signal is a singlet. That is our methyl group. So we know that our methyl group is attached to the sp3 oxygen. That tells us that we have the structure that I drew here. This is the compound, not that. Okay? If we had this other constitutional isomer, our quartet would be the furthest downfield. So signals B and C would switch places if we had this isomer as opposed to that isomer. Okay? So this is how powerful proton NMR is. This is how we can take a molecular formula and IR data, and then we can turn it into an actual structure. After analyzing this NMR data, we know with beyond a doubt that the molecule represented by this spectrum is the one that I have circled here. Okay? So this gives you almost everything you need to know to work the NMR quiz. I'll post the NMR quiz online probably tomorrow, probably on Tuesday. And then when we discuss on Wednesday, when we have our next lecture recording on Wednesday, we will be discussing C13 NMR, and then we'll get into chapter 15, radical chemistry. Thank you.